안녕하세요. Hello everyone, I'm Phil, and I'm a researcher on Google Play. It's great to be here in Korea. You may have heard a little earlier about the Google Play Dynamic Delivery, the new publishing format called the Android App Bundle, and how this will make apps smaller for users. In this session, we'll do a technical deep dive on this new publishing format. We will cover what this new artifact contains, how to build it, how to publish it, and also the different ways that you can test it. We'll also cover how Google Play generates and serves the APKs to end users. Let's start with the format of the Android App Bundle. The Android App Bundle is a zip archive. It contains the files you're already familiar with in APKs, such as DEX files, Android resources, assets, and native libraries. It's important to realize that the App Bundle and the APK are two distinct formats with two different purposes. The App Bundle is purely a publishing format. It cannot be directly installed on the device. It also contains some metadata files that do not end up in the final APKs. Finally, the format of the App Bundle is stricter than the format of the APK. We want to ensure that tools can fully understand what is in the bundle so they can generate valid APKs. Let's open up one app bundle and take a look at what's inside. This is what you can expect, and this should look familiar to a lot of people. Instead of reinventing the wheel, we decided to reuse some of the structure of APKs and only modify what is needed to better describe the files. Let's briefly go through what we see here. The App Bundle has support for having multiple modules, and we'll tell you more about modules in a little bit. For now, just know that the top-level directories in the App Bundle are the names of modules. There is always a module called base, and that's the one we're looking at here. The Androidmanifest Xml file is still present. In your project, of course, it's a real XML file. In the APKs, as you may know, it's in binary format. And in the App Bundle, it's compiled into a protocol buffer format, which allows us to transform it more easily. As opposed to in the APK, in the App Bundle, the DEX files are under a directory named DEX. The Android resources, the assets, and native libraries follow the same directory structure as in the APK. The only difference here is that the XML resources are also compiled into a protocol buffer format instead of the binary format. The file resources.pb is the resource table. It's the equivalent of the file resources.arsc that you may have seen in your APKs. It describes the resources present in your app and their targeting. The .pb extension again means that it's in protocol buffer format, which makes it easier for tools to transform it before we convert it into the binary form in the APK. The assets.pb and native.pb files are the equivalent of the resource table for assets and native libraries. So they only exist if you have assets or native libraries, and also describe the targeting of the files in their respective directories. Let me explain what I mean by targeting the files of your app. File targeting is the description of what type of device or user a given file is targeted for. This is a central concept in dynamic delivery, since understanding the targeting of files means that we can serve to a given user only the files that they need, and this is what allows us to make the app smaller. The App Bundle reuses the targeting model that exists in APKs. You're already familiar with this, so let's run through it quickly. For resources, you could, for example, specify HDPI in the directory name of your resource to target HDPI devices. Or you could add FR to target French-speaking users. Now, we realize that for some of you, assets represent a big part of your app, so the App Bundle also supports asset targeting. We're starting with language targeting, and we'll soon be adding texture compression formats and graphics API versions so that we can serve only the relevant assets to each of your users and reduce further the size of your apps and games. This is how you would create a targeted asset directory. Here we're making use of the hash sign to identify an asset directory that has a targeting. Then comes the key, which defines which dimensions we are targeting. For example, lang for language, TCF for texture compression format, and so on. And then, of course, the value associated with the key. Let's see some examples. Here's a directory containing assets for users speaking French. This is another example of an asset directory, one targeted based on the texture compression format. Now that we've taken a look at the app bundle format, let's talk about how we use this to serve smaller apps to users. I'll explain how we are changing apps, how apps are served to users, so that we only deliver what is needed for each user. Back in Android Lollipop, we added a feature to the Android platform called Split APKs. Split APKs allow multiple APKs to be installed on a device and behave as if they were part of a single app. These split APKs can be installed in different combinations on different devices and can be installed in one go up front or one by one over time. A split APK has the same format as a normal APK. It can contain Java code and DEX files, native code, resources, and assets directories. Once installed, split APKs can all be accessed as if they were in a single APK. Each split APK within an app shares the same package name and version code and must be signed with the same key. Let's take a look at how we can take the Android App Bundle and then generate split APKs that we can serve to your users' devices. We start by putting everything that is common to all devices in the base APK. This includes the Androidmanifest and DEX files, for example. We then generate a different split APK for each screen density. Each split will contain all the drawables that would have been selected by the Android framework on a device with that density. We can then also generate different split APKs for each native architecture. And we can generate a separate split for each language supported by your app, putting each language's strings in a different APK. Together, we call these splits configuration splits, or config splits. Now, when we go to serve an app to a device, we only need to serve a subset of these splits. So if Anthony, pictured here, one of our teammates, has a Samsung Galaxy J5, we will install the base APK, as well as the XHDPI density split, the ARM architecture split, and the English language split. Another of our teammates, Pierre, speaks both French and English, and he specifies both of these languages in his device settings. So for his Pixel 2 XL, in addition to the base and the right density and architecture splits, we will serve both the French and the English language splits to his device. If Pierre then moves to Brazil and learns Portuguese, he might add Portuguese as a language to his device. When he does this, the Play Store will attempt to download the Portuguese language split for each app on his device. If the device is not online at that time, we will download the language splits overnight. And that's config splits. Now, as I mentioned at the start of this section, splits are only supported on Lollipop and above. While this covers 85% of your users, many of you still target pre-L devices, which is great. For these devices, the app bundle still allows us to achieve some of the size savings by generating standalone APKs containing specific densities and architectures. We did, very briefly, consider extending the pre-L approach to cover languages as well, but after doing the sums, we realized that this would get a bit out of control. So, for pre-L devices, we include all the languages in each of the standalone APKs that we generate. When we go to serve the app to a pre-L device, we choose the best APK for that device. So my first Android, a pre-L Galaxy Nexus, will get the HDPI ARM standalone APK. And this is similar to what some of you may already have done in the past with multi-APK. So, putting it all together, the serving picture looks like this. You actually don't need to worry about all of these details about how the APKs are generated. All you have to do is upload a single app bundle, and Play will then generate and select the right things to serve for each device. The dimensions we've discussed so far are only the beginning. For example, I mentioned how the app bundle lets you target assets by graphics API, and we will soon be generating config splits based on this. We will also start generating config splits that take advantage of new platform features in the future. Okay, so now we know about how Play serves split APKs to devices. We'll talk about the size savings that you can expect to see with app bundles. As Tian mentioned this morning, we found that on average, apps published with app bundles are about 20% smaller. That's 20% savings for every new download and upgrade. Let's look at how we reached this number. We analyzed all the apps in the Play Store with more than 1 million downloads. We found that, for strings, we can save over 95% of their size with language splits. For images, 45%. And for native libraries, 25%. This means if every app were to move to the app bundle, we could save approximately 10 petabytes of data per day from app downloads and updates. That's 100 million gigabytes, or 300 million music videos on YouTube. And on top of that, users could see an additional 300 megabytes of extra free space on their device. This means more photos, more music, and more apps on their device. Let's take a look at some actual size savings instead of the averages that have been achieved by some of our early access partners. Now, Twitter were already publishing multi-APK with architecture splits. However, because their app is translated into many languages and it supports multiple screens, they still get large savings, resulting in a 35% decrease in size. Plus, they don't have to deal with multi-APK anymore. Text Plus were not publishing with multiple APKs in the past, but they still achieve 26% savings across all dimensions with the app bundle. Jamo's app is half of its original size, and this is because they have a large native library and supported multiple architectures in a single APK. Okay, now let's look at how you can build an app bundle so that you can start saving as well. The latest Android Studio 3.2 Canary has full support for building Android app bundles. You'll see an option to build a bundle in the Build menu. Generating signed app bundles is easy as well. Just select your app module, product flavor, and build type. Android Studio will build and sign the app bundle for you, ready for publishing. For those who prefer the command line or wish to integrate with automated build systems, the new Gradle Android plugin provides a new set of tasks to build Android app bundles. As you remember, and as you can see here, you would use the assemble task on the command line for building APKs. Now for the app bundle, you will use the new bundle task. Similar to assemble tasks, bundle tasks allow you to specify a specific flavor as well. The bundle tasks will generate an Android app bundle in the output folder with the flavor and build type that you selected. Note that the build artifact is called bundle.aab. Bundle tasks are compatible with signing configs in your build.gradle files, of course. And so a single Gradle task can produce app bundles that are signed and ready for publishing. With Android app bundles, Play will split your app in architecture, screen density, and language, as I've shown you, by default. So no configuration is needed. But of course, we still want developers to have control over their splits. So if for any reason you want to disable splitting by a certain dimension, you can do that using the new bundle block as shown here. So that's an introduction to the Android app bundle, how to build one, and how we use it to serve smaller apps to your users. Next, Tom is going to come up and talk about how to publish and test your app built with a bundle, as well as introduce you to dynamic features.
Thanks, Phil. I'm Tom, and I'm an engineer on Google Play. So you've built the app bundle, and now let's have a look how we can publish it on the Google Play console. First, you must enroll in Google Play App Signing. For those who remember, this is a program that we launched at Google I/O last year. When enrolling, you securely transfer your release key to Google Play. Play then uses this release key to sign the generated APKs on your behalf before serving them to the users. But note that if you keep uploading APKs on your production track while you test your app bundle in the testing tracks, Play will not resign your production APKs. We did this so you can feel confident while trying app bundle on a small audience first without affecting your production users. Once you're enrolled, you can set up your release the same way as you set up your normal releases. So basically, you create a new release, and then drop your app bundle instead of APKs in the same place where you would be dropping your APKs. And once uploaded, you review your release and roll it out. So hit the rollout button, and that's it. And I can't stress enough, no more multi-APKs to deal with. Play has created in the background all the APKs for all the devices that your app supports. Now you've uploaded your app bundle and Play has done the heavy lifting for you. That's great. But wouldn't it be nice to have an overview of what Play has generated? So we have built a new tool called Bundle Explorer in Play Console, which lets you navigate your uploaded bundles. Let's have a look. On the first screen of the Bundle Explorer, you see how much save savings you gained by publishing a bundle. In this example, the app has benefited in 26% save savings. Of course, the save savings is slightly different by the device, so we calculated this using a popular device configuration. You will also find below a list of device configurations and the total size of the APKs served to those devices. Click on View Devices, and you can see which devices are in each bucket. You can even search for a specific supported device by name and download the set of generated APKs that are served exactly to that specific device. This will be super useful when when the user reports a bug about your application and you know their device, so you can get the exact same APKs that Play served to it. Of course, we haven't forgotten about all of you who are using our publishing API, and uploading app bundles is fully supported on that API. You will find all the documentation at developers.google.com/android-publisher. So now we've learned how to build and publish an Android app bundle. But before we finalize the release, let's do some round of tests. We've seen that app bundle is not directly installable on a device. So how do we test it? We first note that during the development, you can install APKs built from app bundle directly on Android Studio. However, for QA teams, we know this is not always an option. So let me talk you about the story of 3 developers, Alice, Bob, and Claire, and how they choose to test their app bundle with their QA team. So let's start with Alice. Alice uses internal test track from Google Play Console. The internal test track is similar to alpha and beta tracks that you may already be familiar with, but it differs that there is almost no delay between the upload of the bundle and the update being available on the tester devices. Going through Play Console, Alice has confidence that what her QA team is getting is byte for byte equal to what end users will get. You can see here how it looks in Google Play Console. To set it up, she creates a list of emails of up to 100 QA testers from her QA team. They received an opt-in link that they need to click, and that's it. As soon as the new version is published on a testing track, her QA testers will get the update. But we know that not all of you have access to Play Console, so let's hear about Bob's story. Bob doesn't have access to the Play Console, and he prefers to test things locally on his machine before uploading anything. But he still wants to test what the end users will get. So what does he do? Well, to generate APKs from bundle, Google Play uses a new tool called the bundle tool. So for Bob to reproduce locally the builds, he simply downloads the bundle tool and writes a few simple commands. Bundle tool has a command called build APKs, which takes an Android app bundle and creates what we call an APK set archive. The APK set archive contains a collection of APKs ready to be installed on devices. Another command called install APKs takes that APK set archive, extracts all the APKs, and installs them on that device. So let's see how these commands work in real life. So here's the command written by Bob, calling build APKs, passing the Android app bundle, and saying where he wants the APK set to be created. And by passing the connected device flag, bundle tool will build APKs only for that specific device that is currently connected to his machine. And if Bob wants to generate APKs for someone else in the team without having a physical device at hand, he can provide the file that contains the specification of that device in a JSON format. You can see an extract of such file here, which provides the information about the APIs this device supports, the supported languages, the screen density, and SDK version. Bundle tool has also the command to generate such device spec files from a connected device, so you don't have to search for them online or write them manually. Also, because Bob wants to install these APKs on a device, the APKs needs to be signed with a private key, so he passes the path to the key store. All the APKs contained in the APK set will thus be signed and directly installable on the Bob's device. And here's the invocation of the install APKs command, which extracts the APKs from the APK set just created by the bundle tool. And they will be installed on a connected device. Pretty easy. So that was Bob and his local testing. Now let's talk about the Claire story. Claire's company has a continuous integration system to build their app. Every day, their QA team pulls a nightly build to test the app on several devices. So Claire also uses bundle tool as well to generate APKs for their continuous integration system. She uses the same command build APKs, but slightly differently to Bob's. By omitting the device spec flag or connected device, she generates the APK set which contains APKs for all possible devices her application can support. QA team can now grab this APK set from the continuous integration server, connect a device, and run the install APKs command. Bundle tool reads the device configuration from the device, extracts only APKs that match the configuration, and installs them. And this is the same selection that happens on Play servers when serving APKs for a given device. One more thing that bundle tool allows you to generate is a universal APK by passing the universal flag. The universal APK is a single APK that contains the files for all the devices. Hence, it can be installed on any device that your app supports. It does not, though, represent accurately what your users will get from the Play Store. But it's a convenient way to pass an APK to someone when you don't know what device they have. Bundle tool is also the tool used to build an Android app bundle itself. Gradle uses it behind the scenes currently. And we will work with other tool chains to integrate bundle tool as well, so that you can build an Android app bundle on any build systems that you use. Finally, we want to be transparent about how we generate APKs we deliver to your users, which is why we have open sourced the bundle tool. You can go today to github.com/google/bundle tool to download the executable or build it yourself from source. Now I'm going to tell you about another way to make your apps even smaller. With Google Play Dynamic Delivery, we are also introducing a way to break up your app into separate features and deliver only those that are needed for each user. Suppose you have a food recipe app and you want to keep the initial download small. You observe that most of your users like to browse for recipes, but only a small fraction choose to add a new recipe and you notice that this functionality takes up a significant amount of space in your app. What you can do is to break that feature out in its own module and serve it only when needed. So we can see how it looks for a user here. So when user goes to add a recipe, the app requests the module to be installed. It is then downloaded and installed and ready to be used just after a few seconds. So which parts of your app should you break out as a separate features? If only a small fraction of users use that feature, that could be a good candidate, especially if that feature takes up significant amount of space in your app. Finally, consider if users can wait a few seconds before using the feature. Once you've decided which features to create, this is how they should look like in the app bundle. In addition to the base directory, there are now also separate directories for each of the modules of the app. The format of these directories is exactly the same as the format of the base that we talked about earlier. And this is the APKs that Play would generate from it. For each module, we will produce a set of splits consisting of a feature split and config splits for that module. We mentioned earlier that split APKs were only introduced with Android Lollipop. For devices with earlier versions of Android, you can mark modules to be fused, and Bundleloop will generate a single APK with these specified modules merged together. Now that we have covered how dynamic features work, let me show you how to create them. To create a dynamic module, all you need to do is to use the new dynamic feature wizard introduced in Android Studio 3.2 Canary. So click on the new module in a File New menu and choose the dynamic module. After typing your module name and clicking Next, Android Studio will generate a new dynamic feature for you. You can also create a new dynamic module manually. We'll start with the Android manifest of your new module. The first step is to declare the module as a new split APK of your app. To do so, you add the split attribute in the manifest and give it a name, which is the VR viewer in this example. The next step is to add a module tag to declare a module and give it a title. This tag is used by the Play Store app to identify the modules of your app. Next, you declare that this module is on-demand module by adding the on-demand attribute. It means it will only be delivered to user's device when requested from within the app instead of at install time. On-demand modules are supported on Android, Lollipop, or later devices. Hence, you also add the fusing tag to instruct Play Console to include this module alongside the base module at install time when delivering to older devices or in the universal APK. Now let's look at the build.gradle files. In the dynamic module, you use a new Gradle plugin called com.android.dynamic-feature. You also add the base module as a dependency of this dynamic module to access functionality of the base module. The only change in the base module is to declare all dynamic modules. This is to instruct Gradle to make the resources stored in the base module available to them. Now I'm going to show you how you can get those modules from within your app with the Play call library. In order to interact with the Play Store to request these on-demand modules from your app, we are introducing the split install API as a part of a new library called Play call library. This is a Java client library that communicates with the Play Store app using IPC. The Play Store then communicates with Play servers to download the splits. Let's have a look at the code. The API is structured using the same task framework that you may be familiar with from Google Play services or Firebase APIs. Installation of splits is coordinated by the Split Install Manager. You construct a request with all the modules that you wish to download and then invoke start install method to trigger the Play Store to download the splits required for the requested modules and install them. For large modules, you'll need to obtain user confirmation prior to download via the install API. You will need to do this whenever an app requests more than 10 megabytes of on-demand modules to be downloaded. The API allows you to listen for updates throughout the download and install process and display this progress to users. In the video of the food recipe app, we use this to show the download progress bar. An alternative option for installing modules that aren't required immediately is to use the deferred installation API. In this case, they will be installed at a convenient time for the user, which means generally where they aren't using the device and are on Wi-Fi and the device is charging. And because of this, we allow you to install much larger modules up to 100 megabytes without requiring user confirmation. The split install API also allows you to manage your on-demand modules. You can see which modules are installed, and you can choose to uninstall modules that are no longer required by the app, freeing the precious disk space for your users. When installing the on-demand module on N+ devices, the app does not need to be restarted. Code is available immediately, and new resources and assets are available once you refresh the context object. However, on Android L and M, installing splits requires the app to fully restart. To avoid this, we include a library called split compat, which emulates the installation of a split on L and M until the app goes into background and we can properly install it. If you are familiar with multi-dex support library, you will set up split compat in a very, very similar way. When you release an update to your app, Play will automatically update both the base module and any on-demand modules that are already installed. So the version of your modules are always in sync. Partners tell us this is something they really like about this model. So to sum up, all the developers can build Android app bundles in Android Studio 3.2 Canary and publish them on Play. I encourage you, all of you, to try it out and see how much smaller your app will be. We'll be rolling out the modularization to developers over the coming months. Currently, all developers can build modularized apps in the Studio Canary and publish them to internal and alpha tracks on Play. However, we'll be opening up publishing in production tracks gradually over coming months. You can register your interest at the link provided. So now I'd like to welcome back Phil, and we will be answering your questions.